final lesson for this section is going to talk about conversion from geocentric to geodetic coordinates. And while this seems like it should be pretty straightforward, it gets a little complicated because the Earth is that ellipsoid shape and not a perfect sphere. If we were converting with their spherical coordinates, we've already talked about how to do that. Again, things are going to get a little bit more complicated because we have to deal with that flattening coefficient and that eccentricity because we're dealing with an ellipse. So we've got this process written down here. What we're going to do is we're actually going to do this in Excel because we're going to have to do some iterations with it. But I want to kind of talk through the steps that we're going to be doing. So the first thing we're going to do is we're going to compute the longitude, lambda. That's going to be tan inverse of y over x. Then we're going to compute this other coefficient, which is essentially the radius or the, if you're talking about the hypotenuse of a triangle that's formed here from the center of the ellipsoid out to our point on the surface. So we're going to calculate that. You can see that's just the Pythagorean theorem. D is equal to the square root of x squared plus y squared. And then we're going to calculate an approximate latitude. So this is going to be our first try. We're going to take tan inverse of our z coordinate divided by the product of d times our 1 minus e squared. Again, so we need to know which parameters we're using so that we can find our eccentricity. Then we are going to calculate an approximate radius of the prime vertical. So we're going to find that Rn using our latitude from step 3, using our formula from before. And then we're going to use now our new Rn that we just calculated to calculate an improved value for the latitude. So this would be considered phi sub 1, if you will, or phi sub n, depending on how many of these we have to do. And so that's going to be tan inverse of, now we're going to have z plus our eccentricity squared times our radius in the prime vertical times the sine of that latitude, and now divided by d. And then we're going to go through steps 4 and 5 until the change between these iterations becomes negligible. And so we have to determine what level of precision that we are concerned with. How many decimal places out you want to go. Maybe it's 1 decimal place, maybe it's 3 decimal places, maybe it's 4 or 5. And so that's something you have to determine. And then you're going to use that formula once you've calculated your lambda, your longitude, and your latitude. Then you are going to use the following formula to compute the height of the station. And so now we've got, again, that's going to be based off of our latitude and our radius in the prime vertical. And for latitudes greater than 45 degrees, we are going to use this formula. So the first formula is for latitudes less than 45 degrees, and the second formula is for latitudes greater than 45 degrees. And again, it has to do with that flattening of the ellipse or the ellipsoid as to why we care about that. So let's take a look at an example, and we're going to go over to Excel. This first example here, what are the geodetic coordinates of a point that has the x, y, z coordinates of 1,241,581.343 and then negative 4,638,917.074. And finally, our z-coordinate is 4,183,965.568. And then again, that's in meters. So let's go over to Excel. Not necessary, but it is best to use some kind of software, especially a spreadsheet, to do some of these calculations. Yes, you can do them by hand, but it's just a lot easier if you can do the iterations in some type of spreadsheet or software. So if you see here, I already have our x, y, and z coordinates, and I also have our a and our b and our eccentricity calculated from the WGS84 parameters. Those are going to be what we need to do our calculations. First, we're going to look at longitude. Again, this is equal to, and we want tan inverse. Now, Excel does tan inverse, known as arctan, as a tan. So that's what we're going to use as our function. Parentheses, the numbers that we want are y divided by x, and we'll close those parentheses. And you'll notice here we get this negative 1.3, which doesn't quite seem right. And that's because it's in radians. So what we want to do, go back up here, we are going to multiply by 180 degrees, and we're going to divide by pi. And with pi, we have to do open and close parentheses afterwards. And you see here, we get negative 75.0162813. So that seems reasonable. This is, as you can tell, these were close to the numbers that we were using for the previous example. We're just now going backwards. For D, again, that quadratic formula equals square root, parentheses, x squared, so we'll grab x, and squared plus y and squared. And close the parentheses, and we get 4,802,184.899. Third step here, we are going to find our approximate first latitude, our iteration 0 here. This is equal to, again, that atan, parentheses, we want to grab z, and then divided by, again, we want parentheses for the denominator because there's multiple things multiplied down there. We want to grab d, and then multiply it by parentheses, 1 minus, and then we're going to go over here to e that we had calculated out to several decimal places here, and then we want to square that. And close our parentheses for the 1 minus e squared, close our parentheses for the denominator, and close our parentheses for the atan. If you forget to do any of those, it'll give you a reminder. So again, this is going to give it to us in radians, so that's 0.72. We'll go back here, multiply by our 180, divide by pi, again, open and close parentheses, and we get about 41.255 degrees. What I'm actually going to do here is I'm going to go in, I'm going to insert a space here. I'm going to copy this down because when we do our calculation for n, we want to make sure that we have our answer in radians. That's what Excel is going to want. So this one here is in radians. This first one here was degrees. So now when we go through and calculate n, again, our formula here is equal to a, so we'll grab that, divided by, we want the square root of 1 minus our e squared times, and we'll do parentheses here because sine is going to have to be squared as well, sine of, and then we grab our latitude here, close that. Again, you can notice how it kind of highlights which parentheses it's closing. It's closing the orange ones now, and then we are going to square sine, and then we're going to close the parentheses on that square root. And we get about 6,387,440. Okay, so now we are going to go back and we're going to go on to iteration 2 for our latitude. Again, I'm going to go with a radian one here. We can figure it out as far as degrees go once we make sure that we have our differences negligible between iterations. So in this case, again, for our first iteration, we want atan of parentheses, we grab z, we are going to add to it our e squared times our previous radius of the prime vertical times the sine of our previous latitude. So make sure you're cool with all of that. Again, we were using the previous radius and the previous latitude. We got our parentheses closed out to the numerator, and then we're going to divide by d. d isn't going to change. And then we'll close our final parentheses, and that'll be our atan. And so you notice here, we are pretty darn close. We've got 0.72003677 and 0.7200366607. So again, very close. We'll go out a few more decimal places though. We'll see if we can get these to line up so that there's nothing showing as far as the difference goes with the decimal places we have showing. N is going to be, and this is where maybe we want to go back and use our dollar signs, because A is never going to change. We're going to go back in here to E1. We're going to put a dollar sign in front of the E and a dollar sign in front of the 1. That means it is always going to grab this cell. Same thing if we go over to E. E is not going to change. We'll put a dollar sign in front of E, a dollar sign in front of 3. The thing that is going to change is our fee here, so we are not going to put any dollar signs there. So we will hit enter there, and now we can kind of just drag this over. Again, you can see these are very close. The only difference, we're off by 0.003. So now we're going to be repeating this process. Also in this one, again, we want to make sure that we're always grabbing the same things. Z, again, is not going to change, so we'll put our dollar signs there. E is not going to change, so we'll put our dollar signs there. And D is not going to change, so B7, we can put our dollar signs in there as well. But our radius B10 and our latitude B9 are going to change, so we're not going to do anything with those. So now we can grab these, drag them out. We've got 6 here, so we'll try it. And you notice here, even if we go out to these next 2, we don't have any change. You can see how there's no change here as far as the decimal places that we're showing. So in this case, we can stop here at iteration 2. We'll come up here, we'll multiply this by our 180 and divide by pi. Again, we can kind of drag that across in either direction and see that, again, we're only off by a little bit between these 2 iterations, and then it levels out after that. So these are going to be the numbers that we're looking at, our latitude in degrees, our radius in the prime vertical. So now we can go through and calculate H. Again, we want to check our latitude. Our latitude is less than 45 degrees, just barely, but we're going to use that formula then. So for latitude less than 45 degrees, H is equal to our D divided by the cosine, and we're going to make sure we grab the angle in radians, close those parentheses, and then we're going to subtract off our radius in the prime vertical. And you see we end up with about 312.4 meters. Again, this is just a rearranging of the formulas that we had from before. So if we want to kind of highlight these, again, our longitude, again in degrees, is negative 75.01628. If we wanted to come down here and put everything in degree minutes seconds, it is possible to do a conversion formula in Excel, but it might just be easier to just say that we are going to take our negative 75 for our degrees, come over here, this is going to equal this plus 75 in this case because we're trying to get rid of it, and we'll put our parentheses around that bit, and then multiply by 60, and we get 0.976. So even that, we're not going to have any minutes in this case. Then we would just take this number again times 60, and we'd get about 58.6 seconds. So our longitude here is, you get 75 degrees, it would end up being 0 minutes, and then 58.6 seconds. They're all negative here because this was negative 75. So if you want to put that together, negative 75 degree, we don't have that symbol, 0 minutes, and 58.6 seconds. Similarly for our latitude, we have this 41 here, so we know it's going to be 41. Then again, we would take whatever that number was, subtract off our 41. Again, we're going to put that in parentheses, and then we would multiply it by 60 to get our minutes. So it would be 15, and then we would take this function, again, put our parentheses here, subtract off our 15 minutes, and again multiply by 60, and we get about 18.21 seconds. So this ends up being 41 degrees, 15 minutes, and 18.2 seconds. So that is our longitude. Our latitude, again, our h in this case is just our 312.4 approximately, and again this is in meters. So we have all of our measurements here. Again, our longitude is going to be west because it was negative. Our latitude is north because it was positive. So this is going to conclude our lesson on converting between geocentric and geodetic coordinates.